Section: Introduction. In this section, we explore the fine-tuning of large language models, LLMs, and its impact on their reasoning abilities. We discovered an unexpected issue. During fine-tuning, models often forget how to solve problems they previously handled correctly. We call this issue temporal forgetting. This phenomenon is common and not limited to specific models. To measure this, we created a new metric called the Temporal Forgetting score, which indicates the percentage of questions that were answered correctly by earlier checkpoints during fine-tuning but were answered incorrectly by the final model. Our analysis of models with 1.5 billion and 7 billion parameters across various reasoning benchmarks revealed that between 6.4% and 56.1% of final errors were once solved correctly at earlier checkpoints. This trend was consistent across different model sizes and training methods. We found that traditional evaluation metrics, which only consider the final model, overlook the fact that many correct reasoning paths are temporary. This suggests that the true reasoning capabilities of fine-tuned models are often underestimated. To address this, we proposed a method called temporal sampling, which samples outputs from multiple checkpoints instead of just the final one. This approach helps recover forgotten solutions without needing to retrain the model. Temporal sampling showed significant improvements in various reasoning tasks, with gains of 4 to 19 points in performance metrics compared to using only the final checkpoint. We also adapted this method for LoRa models to reduce storage needs, making it more practical for deployment. Our findings indicate that a model's true competence may lie in the overall training process rather than a single snapshot in time. We also introduced the lost score, which measures the percentage of questions that were answered correctly by the base model but incorrectly after fine-tuning. This score highlights that even with overall performance improvements, models can lose the ability to answer certain questions correctly. In our results, we observed that while the Open R1-7B model improved its performance on the Olympiad bench, a notable percentage of questions were still answered incorrectly after fine-tuning. Our analysis of various state-of-the-art models showed that the lost score ranged from 6.1 to 16.0 points, with an average of 9.5 points, indicating a significant number of questions that were lost despite overall improvements. To further understand how correctness evolves during training, we evaluated checkpoints at different training steps and introduced two metrics: the ever-correct score, which measures the percentage of questions answered correctly by at least one checkpoint, and the temporal forgetting score, which quantifies the percentage of questions that were correctly answered at some point but incorrectly by the final checkpoint. We also defined events to track changes in answer correctness between checkpoints, such as forget for answers that shift from correct to incorrect and improve for those that change from incorrect to correct. Section Summary. In this section, we reveal that fine-tuning large language models can lead to a phenomenon called temporal forgetting, where models forget previously solved problems, quantified by our new metric, the temporal forgetting score, P_TFS. We also introduce the lost score, P_lost, to highlight instances where models lose correctness on questions they previously answered correctly, emphasizing that overall performance scores do not capture these critical dynamics, and propose temporal sampling as a solution to recover lost reasoning abilities. Section: NeurIPS_2025. In this section, we present our results. In Figure A, we show how accurately the model answers different Olympiad bench questions at various points during the reinforcement learning training of the -7B model. We observe a pattern called forgetting dynamics, where the model frequently alternates between improving and forgetting answers, leading to fluctuations in correctness across checkpoints. Figure B indicates that up to 32.3% of questions in Olympiad bench and 52.5% in AMC experienced forgetting. We also provide the ever-correct score and temporal forgetting score for different models after reinforcement learning or supervised fine-tuning. Notably, many questions were answered correctly at some point during training but incorrectly by the final checkpoint, as indicated by a high temporal forgetting score. This score ranges from 6.4% to 56.1%, with an average loss of about 25 points, suggesting that around 25% of questions were initially solved correctly but ended up incorrect in the final output. For more details on base model performance and additional benchmarks like AME24 and AMC, we refer to the appendix. Our key takeaway is that benchmark questions may fluctuate during training but ultimately be incorrect at the final checkpoint. Unlike catastrophic forgetting, which shows a significant drop in overall performance, our findings on temporal forgetting highlight more subtle changes in answer correctness throughout training, focusing on individual questions rather than overall scores. To address these dynamics, we propose temporal sampling, which leverages the model's evolving state across different training checkpoints to enhance answer generation during inference. Instead of relying solely on the final checkpoint, we generate samples by distributing our sampling budget across several recent checkpoints. We typically select the most recent checkpoints and use a round-robin method to allocate sampling attempts. This method defaults to conventional sampling when only the final checkpoint is used. To evaluate the performance of temporal sampling, we introduce a new metric called pass at k given t checkpoints. This metric measures the likelihood of obtaining at least one correct answer when drawing samples from multiple checkpoints. We define pass at k given t as the expected value of 1 minus the product of the probabilities of not getting a correct answer across the selected checkpoints. We also provide an unbiased estimator for this metric, where we consider the total number of candidate samples from each checkpoint and the number of correct samples. The unbiased estimation reflects the probability of obtaining correct answers based on our sampling strategy. The proof of this estimator's unbiased nature can be found in the appendix. Section Summary. In this section, we analyze the phenomenon of temporal forgetting during RL training, where models oscillate between correct and incorrect answers across checkpoints, with up to 56.1% of questions experiencing this dynamic. We propose temporal sampling, which generates diverse answers by sampling from multiple checkpoints, and introduce a new metric, pass at k t, to measure the probability of obtaining at least one correct answer from these samples. Section: Experiment Setup. In this section, we evaluated the effectiveness of temporal sampling through experiments on benchmarks such as AME 2024, AMC 2023, and AME 2025. We fine-tuned the Quen 7B base model using GRPO on the DEEPSCALER4K dataset, adhering to specific training settings. For each problem, we generated 64 responses using varied sampling techniques with a temperature of 0.6, a top p-value of 0.95, and a maximum token length of 16,384. During the reinforcement learning training phase, we saved 8 checkpoints, which formed our pool for temporal sampling. We compared our results against standard metrics like pass at k and maj at k, where maj at k involved generating multiple samples and selecting the most common answer. We labeled our temporal sampling variations as pass at k with temporal sampling and maj at k with temporal sampling. For best of n sampling, we selected answers based on the highest scores from the reward model. When we set the parameter t to 1, our temporal sampling methods were equivalent to the baseline that only sampled from the final checkpoint. Our results showed that temporal sampling significantly improved sampling performance, as indicated by pass at k with temporal sampling, compared to the baseline. This improvement was consistent across all benchmarks. For example, pass at k with 8 checkpoints resulted in a pass rate over 19 percentage points higher than sampling from the final checkpoint on AME 24 when k was set to 64. Additionally, temporal sampling achieved a 22.5% pass rate with just 5 samples, a level that required 64 samples for the baseline. We also found that temporal sampling enhanced the performance of majority voting, as measured by maj at k with temporal sampling. Using more checkpoints within the temporal sampling framework led to better accuracy compared to the baseline. Specifically, at k equal to 64, maj at k with 8 checkpoints achieved over 21% accuracy, significantly higher than the 13% accuracy of the baseline. Furthermore, we compared our temporal sampling approach against a mixture of model strategy, which combines outputs from different models. We constructed a model pool with our RL-trained final checkpoint, Llama 3.1-8b, and DeepSeek Math 7b Instruct. Our findings indicated that temporal sampling outperformed the mixture approach in sampling performance under the same computational budget. To address the storage costs of saving multiple model checkpoints, we explored using low-rank adaptation, LoRa, for fine-tuning. We saved 8 LoRa checkpoints during the fine-tuning process and evaluated the performance of temporal sampling using these checkpoints. Our results showed that temporal sampling with LoRa outperformed the baseline that only sampled from the final checkpoint for both pass at k and maj at k metrics. This indicates that we can achieve enhanced sampling performance with a significantly reduced storage requirement, making temporal sampling with LoRa a more efficient approach.